Okay, so welcome to this third lecture of the day. Here, I think we will try to combine most of the things that you have learned so far. You are now expert on POD, on DMD, on multi-resolution analysis, on wavelets. And so now, let's say I will try to put the whole thing together in this lecture, okay? So we talk about generalized model analysis and then about multiscale proper orthogonal decomposition. What do I mean by generalized model analysis? Well, yesterday you've seen from the lecture of Professor Smith, at some moment you have a matrix factorization A, B, C, and there are infinite ways you can create these three matrices. And so I would like to spend, let's say, about 20 minutes only on this ABC to make sure that you get the picture. Okay. So this is more or less the content of my lecture. I will start with recalling very briefly, just to make sure that everybody is on board, what is the main scope of this decomposition. Then we'll talk about projection in space or in time, and projection in space and in time. Then we'll talk about the fundamental factorization, which is the ABC that you've seen yesterday. And we will use this to have some fun on the POD and check what happens, for example, if you constrain the frequency content of your data. What happens to the POD if you do some filtering on the data? And the things that we will learn there, we will use them to derive the multiscale POD, which is an algorithm that becomes a POD or an DFT, depending on how you use it. There is a tutorial session. I provided two test cases from time resolved PAV so that you can practice on real data. One is quite large, so don't try on your laptop, at least mine freezes. But at least you can have some data on which you can play with the codes. Of course, I provide all the codes for all the decomposition. These are in the notes, and these have already been uploaded in the folder. We will do 3 exercises. In the chapter, there are more. But in this one, I would like first to go again into this representation problem, and I would like to compare, for example, eigenfunctions with a POD and DMD. Then we spend some time on the course of optimality. You have seen it in action yesterday in the beautiful example from Professor Dawson. Because of the optimality, POD might not necessarily give you the modes that you expect. And then we will use an mPOD on a very simple case. In fact, you find different algorithms of the mPOD there. They are more or less didactic. Typically, the more didactic you want it to be, the less efficient it will be. Okay, so you have 2 versions. Probably soon you will have your third. We don't know. So what is model analysis and why is it interesting? First of all, we're talking about linear model analysis. So we are taking the data and we are breaking it into a linear combination of modes. Each of these modes may evolve in a very fancy way, might be non-linear, but their combination is linear. That is the key distinction between what I'm talking about here and what, for example, Professor Noack has shown yesterday, showing non-linear ways, and we will come back on non-linear methods during the course in a couple of days. So you take the data, I am going to assume that this is a function of space and time, and you break it into the combination of modes. And now, of course, the question is, what do you do with these modes? What are these modes used for? Yes?
N1, so this would be A1, U1, right?
Sitting it?
So you are M1. So your M1 would be the coefficient, say A1 of T.
Yeah. So it's a rank 1 information, a rank 1 version of your data. It is a complete version of the data. Could be anything, yes. Could be spectral POD, POD, mPOD, DFT, you name it, okay? What I'm saying is that each of these guys has been derived under some criteria, and you are isolating and breaking the data into a set of rank 1 information, okay? Now, not all decompositions are ranked based. So if I take 4 modes and I sum them up, I don't necessarily get a rank 4 data, okay? This happens only for the POD. But in general, we are breaking it into some parts, and then we might ask ourselves, what is the purpose of breaking the data into these parts? So you have three main, let's say, application, and depending on the one that you use, you enter into different fields. So for example, one is, let's say, pattern recognition. Well, I should remove classification because the implication is a bit less obvious. But you might ask yourself whether some of these modes represent a coherent structure in your data. And the definition of coherent structure, as you've seen yesterday, is not so obvious. It really depends on the decomposition that you're using. But maybe some of this guy describes the physics and the problem that you have in your data. So here's an example that you will do later. This is one of the tutorials. This is a flow of a time-resolved particle image velocimetry of an impinging jet, and then you use modal analysis to extract, let's say, coherent structure. Let me call them that way, even after the lecture of Professor Mendez. The other application is, well, compression. Do I really need all these modes? Maybe some of these modes describe feature that you are not interested in, that you want to remove, and then you want to do filters. So you decompose, then you clean it up, you remove some modes, and you take only the summation of the guys that you're looking for. Here's an example on which I worked together with Professor Discrete and Professor Janiro, which is about cleaning PIV images. So here we use the POD on a set of grayscale images. You know that the PIV images are composed of a lot of particles moving on. They are quite random, but it can happen. That's the things that you want. But it can happen that you have some reflections that can be time dependent, that can have some strange nature, and they are distributed in space. So you can show that there are POD modes that can be associated to PIV particles and POD modes that are mostly related to background. And so you can keep only the ones for the particles, and you construct a very powerful filter that cannot be constructed using frequency methods. Well, the third application is the topic not of tomorrow, but in today's is model order reduction. So you take a set of PDEs, you project your PDEs into the basis spanned by these modes, and what you get is an ODE that hopefully is composed of few entries, and so computationally speaking, you save a lot of burden, let's say. Here is an example we will also partially see, but this is a lecture on analysis and not very much on the projection that comes afterwards. This is about how to get the modes, not really how to use them to construct reduced order models. So this is the exercise that you will do later, but I'm comparing. This is a velocity profile of a Poiseuille flow. It's a channel which is subject to some pressure pulsation, and so the velocity profile is doing up and down. And you see in the red reduced order model using 3 POD modes, and in black a numerical solution using 1024 mesh points, or using 15 eigenfunctions, because this problem is linear and can be solved also analytically. I have highlighted coherent, undecided, and important, because they depend, of course, on your application, but they depend also on the basis that you choose. I mean, what is important in a Fourier basis might not be important in a POD basis, and vice versa. Okay, so it really depends on what you're looking for. So let's go back now to fundamentals, projections in space and or in time. You have already seen this yesterday, so I'm going to take the tutorial 1. I take an impinging jet. This is time-resolved PIV images. I don't remember what was the number of mesh points or time step, but let's say you have a velocity field on a grid which is nx times ny, and in each point you have a vector, so you have 2 entries. And as you've seen yesterday from the 2 lectures on POD and DMD, you can take this grid and reshape it such that you create a snapshot. Yesterday we've seen snapshots of many kinds, even including different physical quantities, or even different time steps of the same things, as we've seen yesterday in the last lecture. So the point is that you at a certain time step, you have a vector. Okay, in this specific case, the vector will be of sides ns, which is 2 and x and y, because it's a vector, so you have 2 components. If this was a 3D, this is 3 nx and y, and if this was a pressure field, it would just be nx and y. Okay. It's not really important the way you reshape it. Here I'm taking a column-wise reshaping. So I take every column of my field and I put it below. What is really important is that you define, you agree with yourself on how you do that. For that, I find it extremely important to use a matrix linear index, which is what I indicate with the bold, is this I. So let's say that I reshape this matrix A in a column-wise using a Python notation, because now I'm learning Python. You start counting column-wise, right? 0, 1, 2, and blah, blah. Row-wise, it would be the other way. This is important because not all the authors use the same kind of shifting. So it's really important to know which one you're going to use. I will use a column-wise all the time. So you'll see this in my codes. It's always like this. So this is the data matrix that you build, and as we've seen yesterday, every column has a snapshot, so it is a spatial dependency, and every column has a time dependency. And it's a matrix that's going to be size ns and t. And so we meet now our two guys that we will analyze further. I can either consider the kth snapshot, so I take time step 10, for example, or I can consider the time series at location 15. That is a row of my matrix, and the previous is a column of my matrix, okay? I will use this notation to simplify. dk means the kth snapshot, and di means the ith time series. So at the end of the day, as usual, when you do data processing, you end up with vectors. And as we saw today, vectors needs to be represented, and in the moment you represent them, you need the basis. So at the moment, let's not think whether we're taking rows or columns. I just take a vector and I want to represent it with respect to another basis. So as we've seen today, using either a sequence notation or a vector notation, you write your signal as a linear combination of basis vectors. And this linear combination can be written as a linear system, right? So all I'm doing is that all the coefficients becomes what I will call my transformed vector, and I call it B because this is transformed with respect to these bases, okay? This could be Fourier, could be wavelet, could be, you name it. And this is your data. So this is the representation of your vector with respect to these spaces, okay? You mean this? It depends if you start counting from 0 from 1. This, I need the -1 here. Sorry, thanks. Can you write it down? Because we forget. So now the point is, you typically have this guy, and you have these guys because you've decided this could be Fourier, could be wavelet, could be whatever you want, and you want to compute these ones. And everything is linear, so what you will say, doing the transform is just solving this linear system, it's just inverting this matrix, provided that this matrix inverts exist. And what we have written here, in fact, is what we call an inverse transform, which is just a matrix multiplication, okay? So notice that this matrix might not be a square matrix. So I might choose a number of basis element which is not the same as the number of elements that I have in my vector. You've seen that today that a vector defined in terms of a delta functions, of a Cartesian function, is just a vector defined with respect to a basis, which is orthogonal, by the way. And here we are going to represent the vector into another basis. And if the second one is also orthogonal, then we are just doing a rotation, by the way. But the point is that we are just projecting from one vector space onto another vector space. And they might not have the same size, because the one on which you want to project might be smaller, of equal size, or maybe bigger. Do you have questions for the moment? Okay. So very special case is if the matrix of vectors is orthogonal. In this case, B dag B gives the identity. And this happens no matter what is the shape of your matrix. If your matrix is rectangular, this is also true. But the inverse is not true. B dagged is not identity unless B is squared. So what is interesting here is that basically the inner product of every basis element with the other gives you either 1 if you take the same or 0. That is orthogonality, is what we have seen today. And in this particular case, what you're doing is you're decoupling every contribution from the other. Because I can take my vector, dug it with respect to one entry of my basis, let's say B1, and because of orthogonality, I will kill everybody here except this guy, which, by the way, is of unitary length. So the coefficient is just a projection, which is the picture that we've seen today and that I really would like you to keep in mind because we will see it over and over again. So in this particular case, the transform is easy. You multiply by B dugged, you kill this guy, and you go into your transformed domain. But you might not be able to come back easily in the same way. Because if now I multiply this by B, because I want to do this guy, so now I multiply by B, my things. Here now I have B dugged. This is not identity. Not necessarily, at least. Okay? So I make here now a summary on this point about what are the options that you may find. This is just least square problems, or it's just solving linear system if you want. So here is our signal, dimension nu. This is our projected space, dimension nb, and this is our operator that maps one onto the other. You can have three cases. It's a linear system, can have no solution, can have one solution, or can have infinite solution. No solution is what happens when you do reduced order modeling, because in reduced order modeling, typically, you want this guy to be much smaller than that. So there is no solution for that. What you can do is to do for approximation, and the approximation is the projection, okay? We can call this case the skinny family, because this thing is going to be skinny, right? You can have one exact solution. In this case, you are choosing NB to be equal to NU. And this is what you'd always do in signal processing. Because in signal processing, you're really interested in going one way and then the other way. You want to go into one domain, kill someone, and then come back. This is why the discrete wavelet transform has been developed. Why don't we keep with the continuous one? It was already a good tool. It's because then it's very difficult to go back and forth. So in this case, this guy is, may I call it fit? I don't know, it's just a square. The other possibility is what you like in analysis, in continuous wavelet transform. So here you're not really interested in going back. So what you want to do is to correlate your vector with as many vectors as possible to then say, okay, this really looks, at that point, it really looks like this one, and at that point, it really looks like that one, okay? So here you have infinite solution. Your matrix is fat. And basically what it means is that you can pick the one you want. There are infinite. Take a picture of that mentally. In the first case, this is ordinary least square. So I have a vector that lives in a three-dimensional space, but I choose to work only on a two-dimensional space. So if I solve my system using ordinary least square, what you want is that you want a projection, basically. You want the error to be orthogonal to your reduced space, okay? And that is the best solution. If we agree that L2 is the way you should judge best or not. If the things are fit, you stay in the same dimension. And so this is why you have a unitary link between one vector and the other. You can move back and forth the way you want. And this case is visually the following. You have a guy that lives in a two-dimensional space, but you want to represent it with respect to a three-dimensional one. That is like the shadow of whatever you want, but many shadows generates the same thing. So you can use the one you prefer. And what you typically choose is the one that has the least energy. And this is also a reversible process. So I can invert continuous wavelet transform using this trick. Well, we can discuss we can discuss about that. So in this lecture, I will focus on the first two guys. You can get to this from here easily. I just assume that how do you go from this to this? I was supposed to try it somewhere, but I may not there. The invert of this will just be B invert times this guy invert. So this will kill this, and so you get to B inverse, right? Very easy to see that. I even let you see what happens if the matrix is orthogonal. Then this guy is identity and is completely useless to spend time doing all this operation because it's just identity. Now, let's go to projection in space, for example. So projection in space means I take one snapshot, one column of my data, and I construct my basis, which I will call from here on phi, okay? And as you have seen, if I write it in general form, this would be my transformed vector. I don't know if it's annoying to you as much as it's annoying to me, the microphone. Is it okay? You see some noise? Okay, so because I'm breathing, I should stop breathing. Okay, so that is your transformed vector. It's just one snapshot, okay? But the beauty of columns is that you can apply your operator, your matrix multiplication, to all the columns independently. So you might ask yourself, can I project all my data in one shot with a single operation? And the answer is yes. You will just have to do whatever you're doing here to all the columns. And now what I obtain is a matrix in which in every column I have the transformed columns transformed in space, right? So this would be, let's say, the Fourier transform of my first snapshot. This is the Fourier transform of the last, etc. If I'm using Fourier, for instance, okay? Good. And how about the temporal one? Well, it's the same, but if you're lazy enough, since you have rows, you put a transpose. Now these are columns. You do everything exactly the same, and then at the end you transpose it back. So I don't have to introduce you new stuff, okay? And what you get is that, well, you get exactly the same thing, but now these columns are the transformed rows. You agree? The transformed time sequences, okay? So that was projection in space or in time. How about projection in space and in time? Of course, you can do exactly the same thing. The order doesn't really matter. It's a linear transform. And the classical example is the 2D Fourier transform. So here I take for the space, for the column basis, some harmonics, and for the row basis, other harmonics. It's an orthogonal basis, so no need to compute these guys. And if you build your frequencies from 0 to 1, it's also symmetric. So it means that transposition has no effect. And this becomes extremely simple. This is a 2D Fourier pair. Okay, it's a 2D discrete transform. Okay. Now, what does it mean here when I write a transform like that? If I look, for example, at an off-diagonal term of this transformed matrix. For example, if I take M3 and N4, that entry is going to tell us the interaction. What did I say, 3 and 4? The interaction of the third column element, the third basis element of the column with the fourth basis element of the rows. Okay, so this requires a double summation, which is excellent for analysis. If you want to do analysis, you really want to see in how many possible ways you can combine the things. But if you want to do compression, that's not the best way of doing things, and you want to decouple things, not to let them interact. Which take us to the fundamental factorization. The fundamental factorization is simply saying, okay, I want this guy to be diagonal, so that the column basis element 1 is coupled only with the row basis element 1, and no mixed interactions. And for this particular case, when I have a diagonal entry, I will call it sigma. Okay, and so the general factorial transform will be, well, phi sigma psi transpose. Another constraint that typically you add in order to have now these guys being representative of the contribution of each mode is to ask that the basis element have a unitary length. Okay, they might not be orthogonal, but at least they should have unitary length. Okay, and to compute length, it depends a lot on how you compute the inner product. And Professor Dawson showed us yesterday how to do that. You have weighted the matrices if your grid is not Cartesian. Here I'm assuming that everything is Cartesian, right? Otherwise, you have to do what Professor Dawson has shown you yesterday. So at the end of the day, you fix this constraint of diagonality, and here is your decomposition. okay, you have some coefficients. Another typo. Bernd, can you type down this? Sorry. You have a spatial structure which provides a basis for your snapshots. So every snapshot can be written as a linear combination of this guy, and every time series can be written as a linear combination of these guys. And at the end, it means that every mode is an outer product between two vectors and then a scalar that tells you how important that guy is. How many please? Yes, yes, which one? Thank you, thank you, thank you. Okay. Now, besides the typos, next one will spot one will have an even better reward. Do we have questions so far? Okay, so now let's look at this picture. I told you that there are infinite ways of writing this ABC stuff. But this does not mean that there are not important constraints between them. Because I said that the thing in the middle has to be diagonal, right? So you can see this, if you want, in a space view or in a time view. So in a space view, I'm saying that every snapshot is a linear combination of basis element. But now time passes, the snapshot changes, and the coefficient of this linear combination changes, right? They change in time. And who controls the way they change in time are the basis element from the other guy. In this picture, it's a time view, if you want. There's a row view. At every point, you have a time evolution. And this time evolution is a linear combination of your basis element in time. And they are spatially distributed. And how they are spatially distributed is controlled by your basis element that is associated to that. The bottom line is that at the end of the day, the matrix is the same. You're looking at that through different bases, which means that basically you are not allowed to choose phi and psi simultaneously. If you choose one, and you said that sigma has to be diagonal, the other comes as a natural consequence of your choice, okay? Which also means that you can derive a very general algorithm, which I've coded up in Python in the notes and that you can play with. General also means inefficient, by the way, because every decomposition offers you a shortcut to this. And what you do is you define your psi. You can have also the twin of this, which is from the space. It's in the notes, but I will focus on the time view, okay? So I define my temporal structure. So in a non-data-driven method like Fourier or wavelet, you prescribe it. In DMD, you will do the algorithm that you've seen yesterday. You will compute your temporal evolutions. In the POD, you will do it in another way. Yeah, this is just matrices. Matrices don't know if this is convective or not. It's just a matrix factorization. So I take my data D, my temporal structure, and I want to know the amplitude and the spatial one. So what do? I project, so compute my transformed vectors from the time domain, and because of the diagonal, what I get is sigma, phi sigma. And phi sigma looks like this. So you have, in the first column, your phi 1 multiplied by sigma 1. In the second, you have phi 2 multiplied by sigma 2, etc. Okay? But we said that we want bases to have unitary length. So if now I take the norm of this column, I get already my amplitude, no matter what decomposition I'm using, right? So once you have computed this guy, you run your for loop, and you compute every amplitude by taking the norms of this guy, and the spatial one will just be the ratio between them. So you get your sigmas, you get your phi, and you have completed your decomposition. This works for any decomposition, okay? Now, of course, you have shortcuts. For example, if your temporal structure is orthogonal, no point to do this. And in the case of the POD, as you've seen yesterday, the diagonalization step in the correlation matrix already gives you the sigmas. I mean, it gives you the lambda, which are the squared. So also no point to do this normalization. That would be really inefficient, meaningless, I would say. But this is the general picture. So every decomposition fits like that, just because these are matrices, okay? They don't know what is happening there inside. Questions so far? Am I going too fast or too slow? It's okay? Okay, so now some classical families. I said I choose psi. So today I've shown you the psi of the, well, I didn't really show you. I show you that the Fourier modes are in the circle, right? And that all the entries are multiples of fundamental tones, okay? So both every frequency-based decomposition has a temporal structure that has a van der Waals form, okay? The one that you've seen yesterday from the DMD, here you have eigenvalues that can be anywhere in your zeta plane, anywhere. And then you build it, and you have different algorithms that you've seen yesterday on how to compute them. And I'm not going to review them. You know how to compute the lambdas, and this is telling you another possibility to complete the decomposition. In the case of Fourier, it's the same, but now I will fix this lambda to be in the circle and to have multiple, frequencies that are multiple of a fundamental tone, so that they are also orthogonal. I guarantee orthogonality in this case, okay? The price to pay is that you have to assume that your data is periodic. On the other hand, from the POD or energy base, we've seen that you get the temporal structure from K, from the temporal correlation matrix, by diagonalizing that. And I have given you today enough background for you to understand when this becomes this, okay? But I have introduced in a completely different framework, and I think if I have time, I will take my notes to show it to you, because I find it quite funny. So these are my notes, okay? Page 14, if you want to follow. You remember about the convolution? We said that the convolution is this operation. But if we look at that vector-wise, this is a multiplication with a matrix that is called tuplix. It just run over, okay? You have the impulse response and then shifts it and shifts it and shifts it and shifts it, okay? So my filter at the data is y, it's matrix multiplication times u, okay? But I told you today that convolution in the frequency domain becomes multiplication. So I can take now my Fourier transform of the input, Fourier transform of the output, and I will construct. Do you recognize this? This is the Fourier transform of the impulse, which is the frequency transfer function. And I told you today this is a vector, right? So I can store this vector into a diagonal matrix. And now what I can do is what I've taught you today. I look at that in the frequency domain. So if I want to revert, so this guy will be my transform, is this, okay? Hat denotes Fourier transform. Here I have my Fourier transform of u, and here you have your diagonal matrix. If I bring this guy on the other side, I have this. And what I have written is that my convolution matrix is diagonalized by a Fourier basis. This is the convolution theorem, okay? You have learned this during your undergraduate studies, I think. So what it means is that, now let's go back to the POD. Questions? Okay. What happens, do you know a case in which your K matrix will look like a convolution matrix? Is a perfectly ideally stationary test case. In a perfectly ideally stationary test case, the inner product between 2 and 1 is the same as the inner product between 5 and 4, and is the same as 10 and 9, okay, because only thing that matters is the time shift. So in that particular case, your correlation matrix looks like a convolution matrix, and his eigenvectors are Fourier modes. And so in this case, POD is an harmonic decomposition, okay? In fact, you can choose them to be real, so it can become a cosine transform or a sine transform, but we can talk about that over the coffee if you want. And someone very recently took this idea, it's a beautiful paper by Sieber, who simply says, okay, what happens if my correlation matrix should look like this, but is not really like that because of some noise, because of some problems. So he constructs a filter along these diagonals such that he enforces the K to be totally circular, and he pushes the POD modes to go towards the Fourier modes. So quick exercise. This is a pulsating Poisson flow. It's fully developed. It's a 2D. It's a channel, so it's a very, very basic exercise. I'm putting a pulsating pressure pulsation, which is written as a constant times an oscillation. It is governed by this equation. Basically, you have viscosity. It's a linear problem because it's fully developed. So basically, this is just a parabolic, it's a neat equation if you want to see it like that. If you choose the right frequency, you can see some fancy shapes in the velocity profile. If you're in a quasi-steady state, it stays parabolic, but it can be really fancy. And this is an example. So if you non-dimensionalize the problem, you will end up with the Mercy number. You derive the problem in dimensionless form. You can find this in a dedicated notes. You can solve this analytically, and this is a very simple exercise that at least we used to teach before. I don't know if maybe Ben will remove this from the courses. But it's okay. The point is that you construct your basis from the eigenfunctions of this operator. Then you project the problem onto that. You obtain an ODE, which you can solve analytically because it's very simple. And you obtain an expansion, which is analytical, okay, which is coming from the eigenfunctions of the operator, in this case, the second derivative, okay? And now my question for when I go to a discrete world, these also fit in this framework because it's a variable separated problem. And I ask you to compare this with DFT, DMD, and POD, etc. So I think you'll not have time to go through all the details. You have the codes. You can check that I run at a certain moment a loop, and I construct my matrices phi, sigma, psi transpose. And then I take, these are basically the ones coming from the analytical solution. Once I have this matrix, I multiply them, and that is my data. And now I want to decompose this on POD, DMD, and whatever. So this is the DFT from the codes that I provide you. I first compute my psi f by taking the conjugate of the FFT of the identity. And this is just because in the FFT they were too lazy to put the conjugation, so they use directly the conjugation of the Fourier matrix to do the projection, okay? So this is your, psi f is your Fourier matrix. And this is the modal analysis tool, is the function that implements the algorithms, the general algorithm that I gave you before. So all it needs is D, the matrix, and false or true is if you want to have the result sorted or not. We didn't talk about sorting the output in terms of amplitude. So you can choose. This is the POD. You compute the K, then you compute your temporal structure, and you give it to him, and this will give you the POD. This is the DMD. It's just, I ask you to go through the code, and you should recognize all the steps that were shown yesterday by Professor Smith. And at some moment, you get your Van der Moor matrix, you give it to this, and you get the DMD. Okay? Every decomposition fits in this framework. How beautiful is that? This is the eigenfunction. 3 modes. They are orthogonal in space, not in time. In time, they have all the same frequency, just shifted. Okay? That is like a sort of mean flow. These are corrections, higher harmonic. These are 3 modes. POD does not even want me to give to have 3 modes. It tells me the matrix is of rank 2, so I'm going to give you only 2. And here are the ones that it gives me. Okay. In fact, you've seen that the profile was kind of flat in the middle, right? So the POD is telling me, I think you have like a flat profile here pulsating like that, and then some higher order, let's say some corrections on the side to model the fact that the profile is doing this kind of strange effect close to the walls. These are the DFT and the DMD, but I want you to tell me which one is which one. So first row and second row. This is spatial structure, temporal structures. Which one is the DMD? Which one is the DFT? Well, this guy starts in this point and finishes in the same point. I can copy this black curve over and over again. I will have a very smooth periodic thing. The red one does the same. The blue one does the same. This one, they don't do the same. Okay, the first one have been forced and obliged to be a multiple of a fundamental tone. The second were free to take whatever they wanted to take. Okay, that's the main difference between the two. You have a question, Ben? Yeah. Sorry?
You've used the second derivative. You demand a lot. I would prefer an equation just with the first derivative, where you have a convection.
where you have a structure going from left to right through the domain, and this is absolutely not factorizable, but there exist tricks. For instance, if you do the space-time POD, you could encode this structure as one of your space-time varying mode, but it's not factorizable. So I wondered which extra steps would you have to do in your algorithm to include this convecting structure?
I take notes. For the next edition of the course, there will be also this exercise. So now, frequency constraint POD, I want first to show you the cure, and then I will show you the problem, okay? I should do the other way to convince you, but I don't want to convince you at the moment. So the question here is the following. Let's take a POD. I take the data, I filter it, and then I do the POD. And my question for you is, what happened to the spectral content in the POD mode? Okay? Intuitive, you say, if I've removed the frequency from the data, why the POD should have it? And the intuition is right, and I could move to the next topic. But I want to show it to you. So this is your data, your snapshot matrix. As we said, you have time and space. Now I will project into the Fourier basis. So now this is my frequency content in row by row. So the row of this guy is a temporal evolution, and the row of this guy is the FFT of that temporal evolution, okay? So now here I have frequencies, spectrals. And if I want to go back, I just revert to this. Now, this is because, of course, the matrix is symmetric, and we can talk about this later if you want. Now, how do we do this filtering? We've learned today that you need a frequency transfer function, and this frequency transfer function is a vector. But I want a very